from Ian on history matching. So it's kind of applicable to everyone, so just on the theory of history matching and how to go about it. And then we'll split up for the lab sessions. So in here we'll do Python and GPyopt. Next door, Ian and Yanis will continue with history matching, but they'll be doing a practical example for in R. Yep. So they're not clever enough to use Python. So you're not listening.
I'm just off now after that insult. No, that's it. One too many.
Okay, over to Ian.
Right. I see my laptop started without me, so. Right, thank you very much. Thank you very much, Richard, and to all the organisers for the invite. This workshop seems wonderful. I'm having a very good time here. Lots of interesting talks. I hope you feel similarly now. I hope you feel similarly in about an hour's time, but we'll see how it goes. I'm from Durham University. I'm what's called a Bayesian statistician. Okay, so I'm fully into Bayesian statistics, subjectivity, the whole shebang. Okay. Now, first things first, I'm very, very happy to see so many people interested in uncertainty quantification. I'm very happy just broadly with the development in the last sort of 10, 15 years and the way a lot of machine learning is doing some really, really good stuff. There's some nice papers in this area, and a lot of them are looking at adopting and improving Bayesian statistical techniques. So this is great, right? This is a sign, I think, that both Bayesian statistics community and the machine learning community are hopefully onto something when we start doing similar things, right? So this is very encouraging. So today I'm going to talk broadly about these sorts of things. Specifically, I'm going to talk about Bayesian history matching of a galaxy formation simulation. So this is a heavy model. My background is in theoretical physics. I did a PhD and a postdoc in sort of theoretical physics end, sort of string theory, that sort of end. And I had a fellowship lined up in it. But basically, string theory, you have no data. You come up with theories, and you sit back and look at them, and they look beautiful. And then you say, well, maybe in about 200 years' time, someone will build a particle accelerator the size of the solar system, and they might show all my work is rubbish. So I felt physicists were becoming like, theoretical physicists were becoming like artists. Their work is only appreciated after they're dead. So I felt maybe it's time to get into something different. So I now work on complex models of physical systems. If you have a large, complicated model, physical model of something, and it takes you quite a while to run the model, and you want to do a big uncertainty analysis of it, that's my sort of field. So I'm going to talk about that. Bayesian statistics is applied to complex models of physical systems. At the core of that analysis is a Gaussian process emulator. Okay, but there's many other parts that I want to kind of allude to today. Common mistakes in doing this: missing uncertainties. Surprise, surprise, a statistician gets up and starts talking about uncertainties. I will talk just hopefully fairly high level about why we should be careful about these things. And then it is after lunch. You will be tired and sleepy. I've turned these lights down, but I've left the main ones on because let's be silly. Let's not be silly here. There will just be movies of galaxies and pictures of galaxies. So if you don't want to listen to what I'm saying, just look at the damn movies and everyone will be happy and we'll be fine. Then Bayesian emulation, linking model to reality. Okay, I'm going to show how Bayesian statistics formally links your model to reality in a certain setting, and the uncertainties in that link, and why, if you don't do that, you are going to be a little bit in the dark, chasing shadows. Maybe your entire analysis will not be meaningful. Okay, and also it's quite easy to do. And then I'll do this iterative history matching. This is like a global parameter search strategy. It links to many of the talks this morning, Javier's talk this morning, but I'll sort of give our own sort of take on this. And I think there are tricks and traps with this that a lot of people forget, so I really want to highlight some of those. And then visualization of results. Just looking at high-dimensional spaces is not easy. Okay, so in many scientific disciplines, complex computer simulations are employed to help understand corresponding real-world physical processes. This is happening all over the place now. So oil reservoir simulators are used to analyze oil reservoirs, flood simulators to analyze floods. Everyone's heard projections of climate change, right? Most of those are informed by big climate simulators, so it's happening in every science now. We refer to these simulators as computer models, and they share many attributes and many problems. So often they take a long time to run. So I'm mainly interested in complex models. Even a model that takes a second or two to run can be too slow for some standard approaches. But really, if the model takes minutes, hours, days, or even weeks, then you really need a different batch of techniques, of tools. And they also, quite often, these models require the specification of a large number of input parameters that we represent as a vector x. So there might be quite a few input parameters, from a few to 10 to 20, 50, hundreds, even some models with thousands. So an area of Bayesian statistics has arisen to deal with this generic problem, this generic idea. And again, lots of machine learning is now doing this stuff and making progress in this too, and this is all just great stuff. Oh, sorry, let me get rid of this annoying little thing. So we refer to this area as computer models in the Bayesian statistics world, or uncertainty analysis is what we're doing, Bayesian uncertainty analysis. That's the kind of full shebang. Again, this phrase has now been popular because it's come from other areas, applied maths, engineering, uncertainty quantification, the name of this workshop. This phrase I've less preferred in the past because quite often it's meant slightly narrow uncertainty quantification, talking about certain uncertainties. And I think we should be looking at everything, or we should be looking at the big ones at least. Anyway, this phrase is taking over, so maybe there's nothing I can do about that, and that's fine. Okay, so this setup, Bayesian uncertainty analysis, has led to development of a large set of extremely general and powerful techniques. And these have been employed in a range of scientific disciplines. So what I'm talking about today is not just stuff that we've done in this little one area here, and it's just, work there, and would it work for you? No, we've employed this in various different sciences. So cosmology we'll talk about today, but climate science, environmental science, systems biology, epidemiology, the oil industry. Okay, and this is just stuff that I've worked on personally. I've only looked at a bit of this. But these ones here I've spent a lot of time on, and everything I talk about today has been done in those sciences and worked well. So perhaps the science you're working on is similar. Perhaps you're a machine learner who will work with scientists, and maybe you have something similar. Okay. Now, all these areas share similar problems. For example, we might want a history match, which is the idea of learning about acceptable input parameters that ensure good matches between outputs and historical data. I'll make that idea more precise as we go through the talk. But you see the basic problem. We've talked about Bayesian inference being a possible solution, MCMC, ABC this morning, some very interesting talks about this. Various ideas, but the basic problem is quite clear. You have a computer model, which you've coded up or someone's coded up. You want to put some parameters in it. It needs 10 parameters, say. You want to pick those so that the output of the computer model looks like reality. You have some observations on reality, and you just want to say, look, my model is great. It agrees with reality. So what values do you put for your 10 parameters that make it agree with reality? Really, we then want models to do more things. Forecasting, predicting future outputs with appropriate uncertainty. Making predictions is hard and a key part of all this sort of stuff. But then decision theory, deciding on, well, all manner of things, really. You can use your model to make important decisions about the future, such as climate change, how much CO2 should we reduce? Or, for example, just within your science, you might say, well, we have a budget to go and tell some experimentalists to go and measure some more stuff. What should they measure, how much, when, where, et cetera, et cetera. In fact, anything your model might tell you, you might then make a subsequent decision. All these things require uncertainty throughout, incidentally. Many others. So yeah, there we go. All these problems require a careful analysis of all relevant uncertainties. Now, we can never capture all uncertainties, but we can capture the big ones and not fool ourselves into thinking everything's fine when we haven't. So speed is always a problem. I'm talking about complex models which take a long time to run. So of course, how do we get around this? We use emulators. So an emulator is, for example, just a Gaussian process style Bayesian emulator. Okay? And these are incredibly useful because they really help solve the slow model problem. You still have an issue. You still have a slow model that you need to run enough to train an emulator accurately, but it still is a huge advance. So for example, the Bayesian emulators I use here are about 1 million times or even 10 million times faster than the Galaxy model that I'll be looking at. Okay, so that's a 6 orders of magnitude improvement in speed. And that sort of stuff, when I talk to cosmologists, half of cosmologists like Bayesian statistics now. It's really taking over, which is great. Half of them are more traditional and they hate it. But I say to them, you don't need to like it to know what 10 to the 6 means, okay? So 10 to the 6 times faster is just sort of explains itself. So the general problem is as follows. Let's be a bit more mathematical now. So we have a complex and possibly expensive to evaluate model that gives a vector of outputs f of x and requires a vector of input parameters x. So we put these in, that's a vector, and we get those out, that's a vector as well. F is a vector too. Now, here's a subtle point, which maybe Jeremy talked about on Monday, and in fact, I'm sure he did. We have the real system y, that is reality. In this case, it's going to be galaxies in our universe, that we never observe. We never see reality, okay? What do we see? Well, we have imperfect observations z of part of the real system y. So we never see y, so you might say, well, why the hell do I even write it down here? Who cares? I never kind of see it. Well, we kind of care, because reality is what we want to know about, learn about, understand. And we wish to analyze the model and system, possibly to perform scientific inference, to learn stuff, make predictions, decisions, or design experiments. Or we may wish to solve the inverse problem under uncertainty by finding the values of x that give acceptable matches between f of x and z, etc., etc. Now, y is going to be very useful when I talk about the uncertainties involved, because basically we have our model, we have reality, and then we have our observations. And comparing our model direct to observations is a bit tricky. We kind of need to go through reality. And there's two uncertainties in that jump. Okay? So that's why it's there. We're only going to see it a bit later on anyway. There are many traps when attempting to solve such problems, most involving the many uncertainties present. In fact, there's many traps. I would very happily talk about this for just, ad infinitum, essentially. It may feel like that by the end of this talk, but anyway, and there's much to say on this topic, basically. Okay, but here's a big one. This is kind of like a take-home message number 1. I'm not sure how many take-home messages there are. Not too many, hopefully. Okay, so although we may feel that by learning about acceptable values of x, that would be finding where to run our model so that it agrees with some observed data, we may feel we are reducing or quantifying the corresponding input parameter uncertainty. We are. This is only one of many sources of uncertainty present. So quite often you can go to an uncertainty quantification style conference and people will be maybe very interested in this one, or maybe very interested in another one of the list that's coming up. So let's talk about a few of them. There is also measurement uncertainty from observations. I think that's fairly standard. Error bars on your observations and whatever sophisticated model you have for that. Function uncertainty, which is slow to run the model function, that we deal with emulators to get around the speed problem. But emulators have their uncertainty. Remember, emulator is not giving you just a prediction, it's giving you a prediction with an uncertainty. Well, that's fine. You've been learning about that all week. You've done it in the last 2 afternoons in lab sessions. Condition uncertainty. Initial conditions quite often are held fixed. They shouldn't be. That can be easy to deal with, or a bit more of a headache. But boundary conditions and forcing functions being uncertain, that is more of a headache. That requires more like the techniques that Tim was talking about today, that Mark was talking about yesterday. Related to that is solution uncertainty. We can't solve the equations perfectly, so quite often we'll have a continuous system that we have to discretize. Look at any climate model. They run climate models on large grids, which aren't small enough to make current projections as accurate as they want them to be. Stochastic uncertainty. Most models should be stochastic. That's a very kind of general phrase. But there's always stuff in there that you've assumed to be fixed, which really you don't know, and you could noise up. Again, that's another example of what Tim was talking about this morning. But the big one, really, is this last one. Structural uncertainty, otherwise known as model discrepancy. Now, I know Jeremy mentioned this on Monday. This is the idea that your model is missing something. What's wrong or missing? Your model is an attempt to capture maybe the main guts of the problem, but it will have some stuff left out. Quite often what you want to know is my model good enough with just the pieces it has in it? So you kind of want to know whether this thing has to be big or small. But if you are making your model do important things like predict the future, a climate model, I'm sorry, I come back to it because it's just such a clean example. We use climate models to predict the future. We tell the entire world's nation to stop their CO2 output, rightfully in my opinion, incidentally. In fact, we're not doing enough in my humble opinion. And this is based on models, and these models are missing pieces. These models are not true. They're not right, okay? So giving a prediction which you then tell the entire world to act on, you have to give some assessment of uncertainty on that. To not do that, it is meaningless. A prediction on its own without uncertainty is nothing. Okay, so anyway, it's rare to see an analysis that includes all or even the majority of these uncertainties. These really are there. I fully appreciate why people don't put them in, because some of them are a bit tricky, but some of them are okay, some of them are quite easy to put in, or at least you can put in basic versions of them which are quite simple. So if we're using our model for a real thing, it's a good idea. Let's be very clear. It's kind of normal. You listen to a statistician talk, and as I say, I bang on about lots of uncertainties, and I say, oh, guess what? They're dead important. Well, of course they are, because that's what statistics is based on, right? Of course I'm going to say that, okay? But let's be very clear about what I mean. What are the consequences of ignoring many sources of uncertainty? Well, this is the one I'd hit scientists with first. It turns real science into just playing with models, okay? Essentially, sort of real scientific investigation should be at least acknowledging and roughly representing major uncertainties which could change the consequences of whatever work you're doing. You write a paper, you've analyzed a model badly, you write a conclusion saying it looks like more models should be developed of this form or not of this form, and your conclusions are scientifically false. So really, when you don't have uncertainties in, all you are doing is mucking around and playing with models. And that's okay. In fact, model development, you need to do that to start with. But when you start doing real stuff, then you have to, essentially, you have to up your game a little bit. So more specific, overconfident inference. We saw an example of that this morning and previously. So overconfident inference regarding physical parameters and processes. You become more sure about the wrong thing. So Tim showed examples of that with some of his posterior distributions when he hadn't included the noise in the solver. Okay, but that's just one particular example. There's many cases of this. You make doubly overconfident predictions of the future. Why is that? If I've neglected uncertainties when I try to look at my model in the past, and I maybe calibrate, I learn about some inputs, I'm kind of wrong, I'm overconfident. When I then do it in the future, I'm using overconfident inputs to predict a future which I also have not put uncertainty on. So I've missed things twice. So things escalate, and your future predictions become, well, again, doubly overconfident in some sense. This leads to defective decision-making and design of experiments. I think I was just trying to use alliteration there. Anyway, you can imagine this screws up all your decisions, right? And most importantly, to modelers, this leads to misleading model development. If you don't incorporate uncertainties correctly, you can be chasing a particular structure of a model because you're trying to fix something that you shouldn't be fixing in that way because it's just something caused by some uncertainty over here that you've not included. You can also overfit your model. You can get your model to be too accurate when it shouldn't be because there are uncertainties that you've missed. This is perhaps my favorite one, overly difficult optimization, chasing spurious solutions to badly defined objective functions. It's kind of a bit of a mouthful, but this is what we face. We talked about optimization quite a bit. A few talks have been on that, which is great. People optimize various different things in various different ways. If you put uncertainties in, this stuff can be easier because you're doing a more realistic analysis for more realistic situation. Your objective functions that you're trying to minimize can be smoother, can be nicer in certain situations, not always. Making optimization easier. Also, the idea of an optimal solution that you might be chasing, you can be alerted to the fact that that's somewhat unimportant. Statistically, it may not be so useful. You really want to get a class of decent solutions. Well, can it get any worse than that, I think is the question. Well, sort of, yes. People dying. And I don't just mean like statisticians having heart attacks because they see what modelers have done and just go off. Unfortunately, sadly, I mean literally. So tomorrow, Yanis is going to talk about stuff we've done on HIV models in Africa. We've just completed a large 3.5-year project on HIV models in Africa. And how can I say this very carefully? So the World Health Organization has recently changed the guidelines on how to treat people with HIV in Africa, okay? As in they're treating them slightly sooner. Okay, these guidelines have been changed, informed by about 10 heavy agent-based models of how disease spreads in Africa and African communities. Our model was not one of those, thankfully, but it was of comparable complexity, in fact, a bit more complex. I think I can say, this is being recorded, isn't it? Yeah. Can I cover the mic? There are serious questions about the validity of those models, I think I would say. I think that's okay to say. Okay, the decisions based on these models, I would say are of questionable worth because there's a huge list of uncertainties not contained in these. So this really does feed through to real things. Most importantly, I work with modelers and several scientists who I sort of say, well, you know what, we could just put in a bit of uncertainty here because this thing's clearly, wrong or uncertain. And the scientists will quite rightfully say to me, well, look, I'm just playing with my model. It's just mucking around at the moment. It's not real yet. And I say, well, that's fine, no problem. And then the next day, they write a research proposal which says, guess what, give me 3 years of funding because my model will predict what the Earth does in the next 100 years or will predict what disease does in the next 100 years. And I say, but, you just said that you're just playing with models. And they're like, yeah, well, that's talking to you. When I'm talking to funding bodies, I am like modeling the world accurately. Okay, so this is the usual. I'm sure you're familiar with that sort of setting. Okay, well, Bayesian statistics, what does it actually do? Well, it elegantly represents via probability and then incorporates many sources of uncertainty into one coherent calculation. So it has this nice view that any uncertainties that I've listed there and any more you can think of, we have this unified mathematical language of probability that we can incorporate all our uncertainties in and amalgamate them into one quite elegant calculation. Now, there are some calculational headaches, absolutely, but the philosophy behind it is really quite solid. The reasons behind it are really quite solid. Bayesian statistics is not just a list of tricks and tools. It is a philosophy about how you view uncertainty in the real world. It's the extension, if you want to go this far, of like of logic when you are then uncertain. And Bayes' theorem gives you the rule by which you should sort of learn by, in a sense. Now, there are subtleties behind everything I say there, but that's the basic story. So this is not a box of tricks. It's a philosophy which can answer a lot of the tricky questions that I've heard this week. Okay. Oh yeah, just one final thing, as we talked about a little bit yesterday. I hope I didn't sort of cut the questioner off too fast. Bayesian statistics has this nice view of that everything uncertain is just treated on a similar footing. Okay, so we don't portion things off and treat them differently. So we don't have a difference between something that is random and something which is fixed but unknown. Okay, this is an old-style concept which is unfortunately percolated everywhere because everyone thinks as a dice or a coin is random and then thinks of the football results later on today as unknown. Maybe you could think of this as random, depends. Everything is just unknown. There's no such thing as random, okay? So if I roll a dice, I don't know its result purely because I didn't know the initial conditions well enough and I'm not fast enough at calculating the dynamics of a dice rolling. But everything about a dice is deterministic, right? And the only time, as I say, I get changed off that viewpoint is when we start talking quantum mechanics, which is fun in itself. That's a fun philosophical discussion. Everything up from quantum is just fixed but unknown, and we just don't know it. Bayesian statistics views it all equally. Okay, right, that's the kind of warm-up. Now let's just do something proper instead of waffling on about philosophy and whatnot. So yes, we're just going to history match a galaxy formation simulation known as GALForm. This involves this idea of learning about acceptable inputs, that we will define that idea soon, using observed data Z. We use emulators and something called an implausibility measure to cut out input space iteratively. So we do this in a sort of batch sequential way, and our implausibility measure will be our very simple but elegant tool which allows us to do this. We'll discuss the relevant uncertainties. This will hopefully show you what I mean by a full uncertainty analysis. We've teased out many of the uncertainties in this game, and we've put them all into our calculation. Model discrepancy, observational errors, functional uncertainty, etc., etc. This history matching approach is described as completely general and can be used for any model that's relatively slow to run and has lots of inputs. You can use it on a fast model if you want to too. It's absolutely fine. And one of the lab session this afternoon next door, will be just showing you how to do this, talking you through this. And it's very nice to do, and you'll be able to go away and play with it if you want to. If you want to stay here and keep doing Python, though, I won't be insulted. It's fine. I might cry a little bit, but it'll be fine. It'll be cool. I'll do it out of sight. That'll be okay. Here's a nice place to start. I've got lots of references at the end, but this is a nice sort of opening introduction to this sort of area in statistical science. That's a review journal, so it's not too technical. Okay, so let's have a think. Why the hell should we history match? What is history matching? History matching is quite a simple technique, I think, which cuts to the core of what a modeler quite often wants, without going all the way down the route of a full Bayesian probabilistic analysis. So I love full Bayesian probabilistic analysis. I think that's the thing you should do. If your model is good enough and you have a good enough handle on all your uncertainties, then you are ready for a full Bayesian MCMC, or the stuff like Richard was talking about, ABC, provided you can get it to do enough iterations and converge. However, before you're there, you might just want to do something partial. So this is what history matching is. Okay, we're going to find these acceptable inputs, which is the set chi. So the acceptable inputs will be some region of our input space. Our input space in this model is 17-dimensional, so we're going to be searching a 17-dimensional box. The model itself takes 24 hours to run. Okay, that's the level. I'll give you some details on that in a second. The input space that we want to try and find is called chi. Okay, and here's the problem before we start, is that often chi only occupies a tiny fraction of the original input space. Also, this set chi may be empty, so we do not presuppose that any such inputs exist. What do I mean if the set chi is empty? I mean, can I find an acceptable input, which I put in my model, and my model produces output that agrees with data? And the answer is no, I can't. I've searched the space and it's not there. What does that mean? It means my model's broken. It means the physical assumptions that my model relies upon are suspect. Okay? Or there are uncertainties that have I not thought about. Could be the other conclusion. This is the main difference between history matching and the related technique of probabilistic Bayesian calibration, that's the kind of phrase for it in our world, but really that phrase, probabilistic Bayesian calibration, it just means Bayesian inference. MCMC, ABC, like what Richard was talking about, or any similar sampling algorithm that tries to get at your posterior. Okay. Now, the Bayesian, fully Bayesian approach is very, very useful, but it has an implicit assumption underneath it, which is very subtle and quite weird. But it assumes that there is a single best input, X star, somewhere in your input space, and it gives the posterior distribution over the location of that best input. Now that's quite a subtle thing to say. It's like, well, surely I'm just putting a posterior on my input space. What the hell are you talking about? Well, if we take this to a simpler level, maybe we can see the difference. So this is like the murder in the room calculation, okay? So imagine I'm asked the following. I'm told these three people in front of me, my apologies for this example, these three people in front of me, I'm told there's been a murder, and one of these three people definitely did the murder. And I'm asked to investigate who did it, right? Classic Agatha Christie, or Sherlock Holmes if you've got a bit more intelligence. Anyway, so I start asking the three people, and I ask them about their alibis, their motivations, and whatnot, and I start talking like Poirot or something. But maybe I find that this person here has got a rock-hard alibi, and then I find this person here has got a rock-hard alibi. Like maybe they were both with me at the time of the murder. So I instantly say, you did it. Okay? Now, that's because of the initial thing I've been told that one of them is the murderer. But then I ask you, and he said, well, no, I was like actually in France at the time. Really I was. And I go, well, what the hell's gone wrong here? Okay, what's gone wrong is my model is mismatching reality. My model, which was someone's the murderer out of these three, is mismatching reality. History matching is a different question. History matching says there's been a murder, one of these people may have done it, two of them may have done it, three of them may have done it, or none of them may have done it. Now please investigate. So what do I then do? I start asking questions. Rock-hard alibi, rock-hard alibi, rock-hard alibi. Bam, no one's done it, that's it. Okay? Now the key thing is my inference will change depending on which one of those questions I ask. Okay? And especially when you use emulators. Emulators are uncertain about certain regions of the input space and sure about others. So that's me when I've asked the first two people, they give me a rock-hard alibi. My emulator is dead sure for you and sure for you, uncertain for you, but it doesn't matter because I've ruled these guys out. All my probability goes on to you and you get put in jail. Okay, that's the subtlety. Sounds weird. All I'm saying is that subtle viewpoint leads you to different processes. This is not a Bayesian question. This is a kind of modeling question. Anyway, right, you've done very well. You've kind of let me just rant about stuff, okay? Now we have some pictures, some technical stuff about emulation and whatnot, models, but now you can actually see what we're kind of doing. So, just so we're all on the same page, this is a picture of the Andromeda Galaxy. This is the closest large galaxy to our own Milky Way. The picture on the right is a very famous picture, which is the Hubble Deep Field. This picture covers about 2/millionths of the sky, and pretty much every light you see in this picture is another galaxy. Okay, galaxies contain millions or billions of stars, sometimes hundreds of thousands if they're small. And essentially we see things like this in every single blob of this picture. Okay, so what happens? Well, a group at Durham University, where I'm from, the Institute for Computational Cosmology, are interested in modeling galaxy formation in the presence of dark matter. Incidentally, I asked them like how good they are, and they told me they are world leading. So that's their quote, not mine. Okay, it is true. There's three big groups in the world, and they're one of them. So they want to model this sort of stuff. First, they run a dark matter simulation. It's performed over a volume of 1.63 billion light years cubed, and this takes 3 months on a supercomputer. So that's light year is a measure of distance, as we all know. This is a volume. It's technically a bit more subtle. It's a co-moving volume which evolves in time, but let's not worry. I just want to tell you my usual quip about this. The first paper we put out on this, we wrote that phrase in the paper, and the referee came back saying, yeah, the authors have missed out footnote number 3. And we had to politely say, that's not a footnote, that's an exponent. Which is, it's never a good first sentence of your reply to your referee. But anyway, that's the way it goes. To be fair, we had footnote 1 and 2, so they kind of were, anyway. You can imagine the problem. Galform, which is the model we care about, it takes the dark matter simulation and it models this. It models the evolution attributes of approximately 1 million galaxies. So it kind of takes this dark matter simulation, which has the kind of clustering and things hitting into each other, puts more detailed physics on top of that, and does a few more additional calculations. It requires a specification of 17 unknown inputs X in order to run, and takes about 1 day to complete a single run using a single processor. So 24 hours for a single run is what we're sort of talking about here. And it produces lots of outputs that we can compare with real data. So just so I can sort of say, it's quite a big model and it's sort of this, that, and the other. Let's just have a look at, I know for some of you at the back it might be quite hard to see this. This is an example of these sorts of galaxy simulations. This is actually a more advanced one, but it's a more recent one. And this is sort of showing the evolution. They start with a massive box which has slight fluctuations in it given by basic theories of physics, sort of fluctuations from inflation. They let everything collapse. Einstein's gravity takes over, pulls things together. They start collapsing, colliding into each other. You get these strings of gas between clusters of galaxies. And we see this in the sky. We see these strings of gas. And this is one of the things which allows us to select between different versions of cosmology and whatnot. But anyway, you can see this sort of stuff. And this is heavy to do. So that's some of the evolution, some of it clustering, some of it clumping. I'll show another movie of we can fly through the kind of end of it in a second, but that's the sort of stuff we're talking about. You can imagine it takes a while to complete. So, what's our problem? Well, we want to identify this set of good inputs that lead to acceptable matches. Well, I mean, you guys kind of know this, but it's worth thinking about clearly. 17-dimensional input space, which is what we're walking around, is large. If we did the simplest grid-based search, which would be a stupid thing to do, but it's always good to talk about stupid things, and set each of our inputs to its maximum or minimum value. That'd be a full factorial design, a statistician would call it. We'd require 2 to the 17 runs. And all that means is if you had 2 inputs and you put your points down at the minimum, maximum of each input, well, that'd be 4 points at the corners of a square. If you had 3 inputs, that'd be 8 points at the corners of a cube. Well, scale up to 17 dimensions, that would be 2 to the 17 runs. So this would take approximately 180 years to complete on one processor. But just running my model at the corners of the box is precisely not really where I'm interested. I really want to know the guts of my input box. I want to know in the middle. So the naive thing would be just say, well, I want some higher definition. Let's do a grid. Let's do 10 by 10 by 10 runs. 10 by 10 by 10, 17 times. Well, this is really stupid now, but let's just think how disastrously stupid it is. 10 to the 17 runs. This would take far longer than the current age of the universe to complete, which, as we're trying to model the universe, really takes the piss. I keep forgetting I have a microphone. Anyway, fine. Who cares? In fact, won't it be like Sheffield that gets into trouble for this? Yeah, it's fine. That's right. It's like an interview. It's fine. No problem. Amazon. That's right. Amazon. Amazon told me to say. Neil is Neil here? It doesn't matter. Okay. Do you remember that time you got really drunk? No, it doesn't matter. Okay. So what's our solution? Well, obviously, you guys know what the solution is already. You've been trained in this. Our solution is construct a Bayesian emulator, which is approximates the Galfond model and is fast to evaluate. So our emulator is now going to approximate runs from the model, not observed data from the real world, runs from the model, and we're going to replace the Galfond model with our fast emulator and use that to match to observed data and answer all our questions. And as I say, it's approximately, a single emulator is 10 to the 7 times faster. When I batch them up, because there's a few of them, I need to evaluate it, it's a speed increase of about 10 to the 6. So we use the emulator to find the acceptable inputs. Okay, so this is a sort of, in this project, we match the model to modern observations of galaxies. That means fairly recent observations of galaxies. That means up to a certain redshift. And so let's have a look at the structure of the model when it ends. When it ends, this is what it looks like. What we're looking at now, the previous one was looking at the gas and the temperature of the gas. This is now a movie of the density of mass, effectively. It's the dark matter simulation which kind of underlies it. So we see the sort of structure of the model, and this is the level of detail we can get to. I mean, again, these models took, there's about a 10-year construction process to get to this stage, and they've been developed for another sort of 7 years or so after that. That's sort of where we are. And they are quite complicated things and quite beautiful things. And this, as I say, this has all started from just a box with pretty much uniform density in it, with slight fluctuations from quantum mechanics being blown up in inflation in various ways.
Did the simulations show dark matter, or we just?
So yes. In fact, the glowing stuff is just the density of matter. So actually, most of what you're seeing is the dark matter. In fact, yeah, right. That's right. Yeah, one statistician said to me, "Yeah, you should really have dark matter in black." And I was like, "Do you really think that's a good idea?" There's far more dark matter than there is normal matter, so it'd be a real dark movie. Anyway, you see the sort of point. So let's just take that. That's just the bits for people who don't want to listen to what I'm saying. Really, it's nice, pretty. That's all good. There'll be some more nice pictures soon, and some incredibly wise words in between. Not. Okay, let's take that picture. Okay, Galform takes that, models it with more detailed physics on top, produces something like this. Each blue blob here is a young, new galaxy. Each red blob is an old galaxy. There's brighter ones, there's dimmer ones. There's lots of other physical stuff which we can't show graphically. But Galform does something like this. Here is finally our output data. These are measurements of our real universe and the measurements of galaxies. This is this plot on the left. It's called the luminosity function, BJ luminosity function. It corresponds to blue young galaxies. On the left is the luminosity. So on the left we have dim galaxies. On the right we have bright galaxies. The left axis is sort of the log number of galaxies per unit volume. It's actually scaled by co-moving volume and Hubble radius whatnot, but let's not worry about this too much. Essentially we have lots and lots of dim galaxies and very few really supermassive bright galaxies, and an interesting sort of change in the middle. This is on a log scale. Okay, this is log 10, by the way. So this model is trying to capture numbers of galaxies over 5 orders of magnitude. So that's quite a wide dynamic range in a sense. Okay, and this is the same graph, but for those red, older galaxies. Now, essentially, the game is quite simple. We have this observed data in black. We have the Galform model gives us the red run. So the red run is from the output from the model. The black error bars are from what we observe in our real universe. And the cosmologists, of course, started talking to statisticians and said, well, you know, can we get those things close? Are they close? Now, obviously, you do one run of the model and you see that. It doesn't look that good. You then go back to your input parameters. There's 17 input parameters with ranges, which we listed in certain ways. We basically got them to define a box. We got them to define a box by which, if we found a very good match which was outside of that box, they wouldn't care about it. So anything outside of this box they don't care about. That's a kind of one nice lightweight into defining ranges. And these inputs are all cool. This governs the amount of gas blown out of galaxies due to supernova. Supernova explode and they blow out gas from the galaxy. That then takes quite a while to come back into the galaxy. Alpha cooling effect of supermassive black holes in the galaxy. Go figure, I'm not an expert on this. Yield is just like the amount of metal. A bit boring, anyway. But there's lots of cool inputs. So we go back to those inputs and we say, okay, well, let's run the model again. It takes a day for runtime. We get another run. Looks a bit crap. We do 3 days of runtime now. We're hoping we're going to get lucky, and we get this, and it's really, really rubbish. You know the problem, right? I'm stepping around a 17-dimensional space. It takes me a day for each step, and 17-dimensional space is big. So what do? Well, let's run it 20 times. All runs are rubbish. 40 times, rubbish. 60 times, rubbish. When I give this talk to the Galform people who made the model, I don't use the word rubbish, of course, as you can imagine. I forget what word I do use. Disappointing. Anyway. Okay, so what do we actually do? Well, we basically say to the cosmologists, you have a hard problem. How many? And just leave it there, really. We say you have a hard problem. We say you can help. We can help because, of course, we're Bayesian statisticians, and we think we can do anything. We can't really, but we think we can. And then we say, how many computers do you have exactly, and how many can you let us use? So they were very kind. They kind of bought our sales pitch, and they said 500 processors, which are shared with some other users, but not many, and we had quite a high sort of profile on it, so we could use quite a lot of processors. So we then proceeded to analyze this model. We could have probably got away with about a fifth the number of runs as we did, but we thought if we've got them, we'll use them. So we thought, how many runs can we do in a batch? These runs crash, they have to be redone, there's certain complexities, but we thought we could do 1,000 runs in a batch. We could probably got away with this with 200 to 300 runs for the opening wave, but we did 1,000 runs just to be sure. We do this over a space-filling maximum Latin hypercube design, which you guys have heard about. There's just nice ways to fill space with lots of runs. A maximum Latin hypercube is a kind of all-purpose, fairly simple one. There are better ones for certain purposes, but this is a nice kind of easy to start one. We felt with 1,000 points we should be safe enough to get away with that. And let's be clear about what we're going to do. So that's the 1,000 runs we did there. What we're going to do is we are going to take, if you remember, the red runs are what the model does. Okay, we're going to take outputs of Galform, such as this one, and define that as an individual function. So it's a function which has 17 inputs and 1 output. And we're going to emulate that function. Okay. Now, there's various choices for what we could have done here. We could have combined these outputs in various ways. There's lots of nice stats ways to dimensionally reduce combined outputs. There are advantages to choosing the raw output of the model. Quite often it can be easy to emulate. I'll talk about that soon. So we're going to emulate the red runs so we can understand them, find where they're close to the damned data. What I mean by close, I'll define precisely soon. So, the nice thing is you guys have been doing emulators, so you know what an emulator looks like. Here's an example I'll give throughout the talk so you can get a feel for the theory before we apply it to the full galaxy model. Here's one input parameter. Here's the output of my model. I do 6 runs. It takes me 6 days. I use my emulator to fill in the gaps. Okay, and my emulator evaluates in the thousandths of a second or faster, and everything's lovely. So my real question is, does that function match this observed data? If you imagine I have one observed data point with error bars, well, on this plot, where I've got this input parameter that I'm searching over, that error bars, they get smeared out into 3 lines. And the question is, when does this function get close to this interval here? And the answer you can say is, well, when my input parameter should be around this region here. Okay, now we're going to get back to that. Let's just say a few words about emulation. I think you guys have heard a lot of good stuff about Gaussian emulation, Gaussian process emulation. I'm just going to supplement that with a few sort of additional details. There is discussion in the computer model literature about the best way to emulate stuff. And essentially, depending on whether you have low numbers of runs or high numbers of runs, depending whether you're in high dimension or low dimension, there are some additional choices that can get you a better emulator. So here we had quite a few runs, but we are in moderate size dimension. So what we did is the following. We represent our function f indexed by I. That just means one of those dotted lines at one particular output. And I said, well, I'm going to write this as a Gaussian process, but what I'm going to do is I'm actually going to pull out the mean function as a third order polynomial in some of the inputs first. I'm going to have the second piece, which is also now a Gaussian process, and a third piece, which is a nugget, which is random noise. So this is a sort of slightly more advanced structure for my emulator. Now, why have I done this? Well, look at this. XA here are what's called active inputs. Quite often in a model, you might have several inputs, but the outputs you're interested in, for an individual output, say, it may not depend strongly on all of your 17 inputs. It may depend strongly on, say, 5 of them, and moderately on 3, and a bit on 2 more. So for an individual output, that's not a 17-dimensional function. It's more like a 9-dimensional function. So the simple techniques you can do to pre-scan inputs to start with per output and find the sets of inputs which are active and put these in here. Then, most importantly, I have a Gaussian process. This whole thing, I could combine these two together into one big Gaussian process, incidentally, which would be very much like what you've looked at. But it's a Gaussian process defined over a smaller dimensional input space. This is a Gaussian process term on its own. So essentially, I've dimensionally reduced differently between different outputs. The fact I have dimensionally reduced, I bring in some extra noise because I have these extra inputs now which I've kind of ignored, but they're still there. So I represent them by a nugget term which has no structure and just a bit of noise on it. This allows me to dimensionally reduce. I'll say a bit more about this in a second. The covariance structure of this guy, we use squared exponential. This can do okay in moderate sizes of dimensions. It has some dangers. You can be a bit too sure. Excuse me. However, when we fit these polynomials, we can look at these polynomials, and actually we find that they capture quite a lot of Galform's behavior. So for example, if I just looked at a bare model like this, in fact, that's like a polynomial plus some noise. That's just like a regression model, right? So I can fit that quickly, have a look at it, say, actually, this regression model is explaining, say, 90% of the behavior of Galform. Well, that's quite good. I've captured 90% of its behavior in a very simple mathematical expression with very few parameters. And then my Gaussian process is going to suck up the rest, the deviation from the polynomial. So that can be quite a nice strategy. And it can bite you sometimes. It can be all right in others. Anyway, my emulators, Gaussian process style emulator, I'm not going to say too much about the details of that. And what they give me is they give me an expectation for f and a variance for f. I've implicitly hidden the conditioned on sets of runs of the model, et cetera, et cetera. But essentially, they give me an expectation and a variance. So that's all cool. So, again, what do we do? Well, you've seen this week. We do a set of runs of the model, n runs. This gives me data, n runs of Galform. Here we had 1,000 of these. And then I can use Bayes' theorem. Again, you've seen this, so I'm just going to skip through this quickly. But you can use Bayes' theorem to update this, and you get your Gaussian process style emulator updated by these. That's all lovely. That's kind of like the standard Bayesian paradigm for constructing an emulator. There is another alternative way to do this. Gaussian processes kind of rely upon you, well, they implicitly ask you to define a distribution, a normal distribution, over all this sort of space. And you may or may not believe that. There is a slightly more hands-off way you can do this, which again, I'm not going to spend time on, but it's called Bayes linear statistics. This is kind of like a linearized version of Bayesian statistics. And it rips out the core of a Bayesian calculation, which is what happens with the moments. Prior expectation, prior covariance, posterior expectation, sort of. And it rips out the core behavior of Bayesian statistics and tries to just use that. The nice thing is it involves no MCMC and no heavy calculations, just linear algebra. This can work very well in certain situations. In other situations, it can be less accurate. Anyway, that's all fine. There's our emulator. Now we know how to do it. You guys are experts in that already. However, this relates to a question we had earlier on today. And this is sort of general guidance for emulation. We still have a choice as to which level we emulate at and what to emulate. So, for example, we may attempt to emulate all model outputs, either multivariately or univariately, or say some objective function that combines them together, for example, like a likelihood or log likelihood. So I could wrap all my model outputs together and emulate that. I could have part of them together, emulate that. I could emulate them individually. I could think of some combinations of them. So you can choose where to emulate at, from the model here to summaries of the model over here, like likelihood, for example. Now, those choices are important. So a critical problem is, often for complex models, we cannot initially emulate several of the outputs accurately. Some outputs can have hard behavior to emulate. So this may be because the model behaves erratically in scientifically uninteresting parts of the input space. These may be unphysical, or at least far from that region of interest chi. So what do I mean by that? I mean you have a box of inputs. In certain corners or certain regions, your model just does crazy stuff. Okay? If you wrap all of your model outputs into one big objective function, you'll be trying to emulate an objective function which contains some crazy behavior of your model. And that may be hard to do. You may be lucky, it may be smoothed out and it's not too bad, but it may be very, very hard. So emulating all model outputs in the first iteration and combining into some calculation like a likelihood or like an MCMC or equivalent can be a bad idea. This is more like a warning. In low dimensions, you should be able to get away with it. In moderate dimensions like here, it may be a real problem. So emulating an objective function like a likelihood can be difficult in high dimension. There's another subtlety to this, and it's to do with active inputs. So often some model outputs, fi of x, are easy to emulate. So when I look at my Galform outputs, actually the ones on the left are easy, and the ones on the right are easy, and the ones in the middle are hard. Where that break in the luminosity function happens, every bit of physics is talking to that break, where the only one part of the physics talks to dim galaxies and another part to heavy galaxies. So I can emulate at the beginning of the luminosity function at the end very easily, and in the middle it's tough. And that's because at the beginning and at the end they depend upon smaller sets of inputs. Okay? So if the numbers of active inputs, xia, for each of my outputs are not too high, we then have the task of emulating a collection of effectively lower dimensional outputs. So if you think about it, I can wrap everything up into one and have a one-dimensional function which is truly 17-dimensional. As a 17-dimensional input and a one-dimensional output, that's what a likelihood is, or comparable objective function. Every sequential design talk we've seen this week has used one function which has wrapped up everything they care about into one. We can break this into pieces and say, actually, there are pieces that I can emulate incredibly easily. And those pieces are like 5-dimensional. This one's 8-dimensional. This one's 6-dimensional. That's far easier, like really far easier. However, any objective function will have as its inputs the union of every active input, most likely. So it will be high dimensional and hence harder. We have a long paper on this sort of stuff, and it was a discussion paper, and we went over this in detail. So one of the references at the end, you can read a large discussion about this. The discussion is kind of all right. It's worth reading more. The paper's quite technical. The discussion's quite cool. There was some blood spilt in the discussion, so it's kind of worth reading just to see, how nasty statisticians can get. We weren't nasty. We were just right. Anyway, that's beside the point. Okay, so that's kind of one warning. Okay, right. Back to our task. We've got to use our emulators. We want to link the model to reality. So we need to officially have some statistical model that does this. So we're going to use what's called the best input approach. Here we say we have our model F. We have reality Y. If you remember reality. And we say our model is going to be hopefully good, but it's not going to be perfect. So we're going to evaluate it at some possible best input x star. And we're going to say that's going to miss reality by some amount epsilon. And epsilon is called the model discrepancy. That's the kind of wiggle room for our model not being perfect. And we'll talk about assessing that in a second. We then say Z is observations of reality with observed error E. And again, E is going to be, that's just a random variable which represents the observational error process. And we can make these models more complicated if we want to, but this is a nice model which captures the main guts of it. So our model is not quite right, and we need to respect that. What the hell do we do with this? Well, often scientists are able to specify something about the expectations of these two things. Quite often they're 0. And the variances of these two things. Remember, this guy is a vector. It's a vector of outputs, the same number of outputs as I have to emulate. So we need to say something about this. Well, in this thing here, I won't go through the full details, but we spent quite some time estimating these uncertainties quite carefully. There were 7 in total. So for the model discrepancy, there were 3 pieces. 2 we could do with further experiments of the model, varying things in the model that had been kept fixed. Okay, and we said, well, you can't keep it fixed. We'll vary it a little bit, do a little experiment, and take a covariance matrix from that. And there was finite size, volume size effects that we could calculate roughly and work out. And then there was an expert assessment of other things that have gone wrong with the model that are missing. And basically for this, we talked to our experts about what goes wrong with the model, and to cut a long story short, the models either overestimate or underestimate numbers of galaxies. That gives you a correlated model structure. And it gets the ages of the galaxies wrong. So you get too many red, too few blue, or vice versa. So this gives us a kind of parameterized structure for our model discrepancy covariance matrix. This is a lot of details to be throwing at you. All I'm saying is you'll be able to see these slides afterwards. It's in the papers. We are able to get a structured idea of why our model misses, okay, to a reasonable extent. Then we gave our expert cosmologists, we gave them an elicitation tool where they're able to make fake luminosity functions and move them all around and say like, ooh, I don't like that, or that one's okay, or that one makes me feel queasy. And then they're able to get the parameters for their model discrepancy by playing around with these. So what we're trying to do is we're trying to capture their expertise when they look at a function from their model and they say that's a bad match, and they look at another one and say that's a good match. We're trying to capture that expertise. Because most modelers have a lot of strong feelings about this, they don't quite know how to turn it into mathematics. But we can do that. It's not too bad. Okay, measurement error. There's 4 kinds. We went through this in detail. Lots of different complicated types. Lots of them are correlated. But we sort of went through that and everything seemed fine. So, one more technical thing to say, and then it's pictures from here on out, pretty much. What do we then do? We then take everything I've told you so far, the emulator, which is this bit here. That's the expectation for my Galform function, given the runs I've done. That's the expectation of the emulator. We look at the difference between it and the observation Z. Those are the black dots. And we take this and we divide it, we just standardize it by all the uncertainties that we have. Here is my emulator uncertainty. Here is my model discrepancy. Here is my observed error. This implausibility measure is very, very useful. This helps us to decide which parts of the space we should search and which parts we shouldn't. So large values of my implausibility function imply that we are highly unlikely to obtain acceptable matches between model output and observed data at input x. Why is that? Well, basically, if this thing is large, it's saying that we expect the model to be so bad compared to the data, even given the uncertainties we know about, that we think x can be discarded. And I can cut x out and not worry about it anymore. But small values of I of x do not imply that x is good. I of x just tells me when things are bad. It doesn't tell me when things are good. For something to be good, I need to match every single output well. For something to be bad, I just need to screw up on one output, and that's a lot easier to detect. So this is me breaking a likelihood into small pieces and using each piece individually. Easy to do and quite efficient. Okay, we can combine these via maximization first of all. We can then later on, after several iterations, we can combine them multivariately. This is more like a Mahalanobis distance. Well, that's what it is. Which is a bit like a multivariate normal likelihood, but not. There's an important piece different, but it's of that sort of ilk. So you can wrap things together later when you've done a few more iterations. So there's my emulator, there's my observed data. That's now my implausibility function. My implausibility function looks like this. So this is a bit like the sequential design talks this morning, Javi's talk, which was all very nice. He showed a lot of plots like this and showed some functions that he was either going to maximize or minimize. Here's one we're going to minimize. Well, we're not going to minimize, sorry. We're going to look at it when it's small. A key point here is because our errors are meaningful, I can put some scale on this graph. Any value below 3 is a value that I need to look at further. Anything above 3 is probably rubbish. This comes from Puckelsheim's 3 sigma rule. It's a very powerful rule. It says that any unimodal distribution, doesn't matter what the skew, tails, anything you like, if it's unimodal, it will have 95% of its probability within 3 sigma. Okay? If you say something's normal, you say that statement with 2 sigma. If you just say it's unimodal, and it can be totally skewed. So a distribution like this will have 95% probability within 3 sigma. I've not worried about distributions too much, but I can put this 3 down as quite a reasonable kind of cutoff. No fuss. So there's some colors. Green means low implausibility. Please look at me further. Red means discard me because I'm rubbish. Now, we could just stop here and I could just say, well, we're done. Well, of course, that would be quite crazy. What we want to do is a sequential batch style approach. I've just got a few more pictures. You know the deal. So I say that as I go into a slide with no pictures on it. But anyway, I've just got a few more pictures and a few more slides. We're almost done. 5 minutes away. OK, so often the set of acceptable inputs chi only occupies a tiny fraction of the original input space. And therefore, we don't want to use a single one-shot space-filling design, as we'd waste a lot of runs in implausible parts of the space. There's that word, implausible. Red, bad. Okay? So obviously, we're going to do a series of iterations or waves, designing in ever smaller, non-implausible regions of the input space, i.e. batch sequentially, like we learned about this morning. And I think that point is fairly obvious. To do things sequentially and in batches is how computers run these days. You rarely send off one run and then wait and analyze it. You send things in batches. But doing things in iterations or waves, as we call it, that's fairly obvious. What is less obvious is the next point, although someone did ask something related to it this morning, which I was very happy about. However, we would also perhaps not want to use the same statistical form for the emulator across all waves. I'm going to set up an emulator. I'm going to zoom into a small part of the space, do another set of runs, set up another emulator, zoom in more. I'm now in a much smaller part of the space. Do I want to use the same emulator that I did at the beginning? That is not obvious to me. Okay? In fact, I'd say mostly no. Do I want to refit the parameters of the emulator? Probably. Do I want to have a really different structure of the emulator? Maybe. Different active variables, different polynomials, different parameters. And this is less obvious. And in fact, so therefore, we might fit, and we'll fit emulators of different structure and complexity at each iteration. I'm going to emulate more outputs. I'm going to emulate in more detail, larger numbers of active inputs. And this has implications for the full design calculation. Because when I know I'm going to do this in advance, that makes the design calculation harder in one way, but it also says I kind of, in some sense, need to worry less. Just go ahead and do it, and worry not so much about detailed design calculations. OK, so that's all fine. Here's the iteration. In fact, let's jump to this one. That's my first wave of runs. I then do a second wave of runs, which looks like this. So you've seen these sort of pictures. My emulator gets resolved. My implausibility measure does this. But here's another nice feature of this whole approach. Our errors are meaningful. Our observed error and our model discrepancy is meaningful. This naturally gives me a stopping criteria. Okay? Doing sequential design of runs, the stopping criteria can be quite an issue. When do you stop? When do you know you've searched enough? Well, I'm actually on a scale here. These errors are meaningful. So as soon as my emulator errors are far smaller than my observed error and my model discrepancy, I know to stop. Okay? No more runs here is going to change this picture more than about 1/10 of a pixel, because my emulator is really, really well nailed, and my observed errors are now dominating, and I can do nothing about those. So including uncertainties gives you the natural place to stop, and to stop worrying and proceed. Incidentally, here I've used the same emulator here as I have in wave 1, but actually I would fit a fresh emulator to these points here, is the process. OK, great. That's the algorithm, but it basically just does what I say. You do a batch of runs, you emulate, you zoom in, you do another batch of runs, space filling at first. In later waves, you might want to be more detailed, try and do runs located close to where the posterior is. In the first few waves, just space filling, et cetera, et cetera. So let's just show that in action. Here is now the results for Galform, if you can cast your mind back to where we started. 17-dimensional galaxy formation model. Here is 2 of the dimensions, 2 of the input dimensions. This is a projection of that implausibility function. I just blitz my space with millions and millions or billions of evaluations of my emulator. I calculate the implausibility at each point. I can do that very, very quickly. I project it down into 2-dimensional pictures so I can show it to my scientists. And I've minimized the implausibility. So what that means is if I see a red region here, it doesn't matter. If I choose this variable to be here and this variable to be here, it doesn't matter what I choose for the remaining 15 input variables. I cannot rescue the situation, and Galform is definitely a bad match for this region of these parameters. This is how we can interpret this. So that tells the cosmologist definitely bad here. It doesn't matter what you do with all the other 15 inputs. But that's just the wave 1. What I then do is I do a second batch of runs, and this picture then evolves to, so I do another batch of runs just in the green region, and this evolves to this, and then I do another batch, and then another batch. And now I can tell that my emulator errors are smaller than my model discrepancy and my observed errors, and I know to stop. It's quite hard to know when to do that. And this is now a projection of a small thing. It's about a thousandth of the input space. And this is a small object in high dimension, which I project down, and you can look at the shapes and interpretations of it in input space. So here's another one. One wave analysis would only give me this. So doing batch iterative sets will, of course, give me more detail, and I get this sort of picture here. But what we're looking at here is the silhouette of a blob in a high dimensional space. That's quite useful for determining where good runs are. But it is the kind of silhouette of the region. So what we might want to do is replot these showing the thickness of this blob here. So what I can do is I can show what we call optical depth plots. These are just straight through the depth of this object. So this shows how thick the object is. That's the same picture as before, but now I can see this, and I can say that there are many, many solutions here which are acceptable. So many choices of my other 15 parameters, aside from these two, which are acceptable. But over here, there are some good solutions. It's just there's very, very few of them. Now, when scientists stumble around input space and try and find solutions themselves, they will overwhelmingly likely stumble towards regions here and miss regions here, even though there may be good fits here. There may just be lots of mediocre fits over here. So you can kind of interpret these in lots of different ways. OK, fantastic. Why does this work? It works, well, basically, when we zoom in, our emulators get more and more accurate. When I zoom into space, my polynomials in my emulator get more accurate because my function gets smoother. My Gaussian process part of the emulator gets more accurate because I have a higher density of runs. In later waves, I can identify more active variables. So I had an output in wave 1 which maybe had 5 active variables. In wave 4, it has 10 active variables. That's because once I've zoomed in, I've sort of constrained the effects of some big dominant variables, and I've now cut them down, so now I can pick a few more subtle variables and have a more sort of rich emulator, if you will. So my emulators get better and better and better, and hence number 4 is really, really important. I can then emulate tricky outputs that I could not emulate before. So those outputs in the middle of middle of the luminosity functions, I can emulate them accurately and bring them in. So now at the end, I emulate everything, and I can wrap it together and put it in a likelihood if I want to, but only at the end. I have to do all this stuff first. Fantastic. Things are fast enough that I can do 3D versions of implausibility and optical depth plots. At this point, I can then, if I want to, proceed to do a fully Bayesian calculation within this region. I can do like an MCMC on this if I want to. This is a sort of a pre-calibration process one can view it as. Here's a fun picture. That's a 4-dimensional slice of the space. So the emulators are fast enough you can start teasing apart this space in a big way. If I had to show you an apple, a 3D apple, but I was only allowed to use 2-dimensional pictures, I may slice that apple 10 times and lay out an apple in a row of pictures. That would show you a 3D object using 2D pictures. Well, this is the same thing. I've sliced my region, but I slice it now in 2 directions because it's 4-dimensional. And there's lots of intuition we can take from these plots. OK, let's just cut to the chase. We showed the cosmologist this picture saying, here's parts of your input space. We think you can find good runs wherever there's green. It's a twisting hypersurface in a 17-dimensional space. You can find good runs there. And they said, well, we find that slightly unbelievable. We said we find that slightly questionable. They'd searched for quite a long time. They'd found a mediocre fit up in the top right-hand corner. And they did not think there were runs which would fit all the way down here. So we just did a batch of runs in that green region. And then we handed them hundreds of runs which were a better fit than ones that they'd seen before. So this is the point where I say you don't have to believe in Bayesian statistics to just say it predicts this, we run this. These are now runs. They're colored by actual just distance from run to data. No emulators involved. If it's something's green or yellow here, it is just a good run. So we just handed them these runs and said, look, there was our initial wave of runs. There's the data. That's our wave 2, wave 3. We did a wave 4, then a final kind of batch of good runs. And this is what we got. So we handed them several hundred runs which were like this. And that's a nice place to be, because people don't always buy into every single technique you're using. But if you just give them this at the end, everyone's happy. OK, that's the other graph there, similar results. I think I'm already over time. I'll just say this stuff we're doing, it's quite easy to learn. It's not hard. It's emulators combined with implausibility functions. But I think it is the most efficient way in to higher dimensional parameter searches. OK, thank you very much for your patience.
How many runs in your peak model did you have to do? You said 1,000 in the first step. How many?
We did 1,000 each wave. We slightly increased each wave. We did like 1,200 in the next, 1,400 in the next. So I think it was about 5,000 or 6,000 in total. However, we did that because we had the resources.
Okay.
So I think I would confidently say we could half that. I think probably a third of that would be quite reasonable. So that level of numbers of run.
How long does that take to do? I mean,
Yes.
the
So
users you've had?
doing sets of runs on this model, we had 500 processors. Also, it should have been 2 days all in, but several runs crashed for various reasons. So it was about a week for a batch of runs, and then we would analyze things. But we did this project. We then discussed all the uncertainties and everything as we went along. So we did a batch of runs, showed them to the cosmologists, constructed emulators. With our polynomials, we could show them the structure of the emulator. We could say, look, these inputs are informative for these outputs. Does that make sense? They were like, in some cases, yes, in some cases, no. And we checked everything was OK. And then we would do the next wave.
Okay.
So, I mean, the turnaround time for the analysis of setting up the emulators is not too bad. You can set them up in a day, really. But it's quite good to set them up, talk about them, show them to the scientists.
It's about a week for each wave.
Give or take, yes, yeah.
Oh,
So how do you find the active inputs? And also you saying that you started off with a fewer amount of active inputs, and then am I right in saying that as your emulator became better essentially, because you closed it at a different area, then you could start to use the less significant ones if you're looking at a larger scale? How do you choose them in the first place?
Right, well, there's various techniques you can use. Thank you. Your description is perfect. I'm happy that you can describe it so well. Yes, so there's various things you can do. We had quite a few runs here, so we can just use classical statistical techniques, so linear model selection techniques. We have enough runs here that I can just sift through these runs using, say, fitting regression models of straight lines or of quadratics, and seeing which inputs are picked up as being in some way predictive, in some way important. Okay. That's correct. So what I do is I sift through the runs to see if any linear term looks like it's predicting the outputs in any way. Okay, and the active ones normally will jump out as being obviously predicting something linearly. Like the only chance they would look like they're not doing anything there is if they, for example, were having a big quadratic effect on the output, which was perfectly symmetrical with the range we started on. Okay, which is unlikely to be. Any function which looks like this, slightly skewed quadratic, will have a linear effect, which classic linear model regression techniques will pick up. The reason we use those are classical techniques. They're not Bayesian, but they're just a fast way of scanning through to pick up things we should then build a Bayesian detailed emulator based on. Okay.
Throwing away things early by throwing away active inputs which might actually be relevant.
Well, the key thing is those inactive inputs, as we then call them, contribute into the nugget term. So we have this nugget term which has no structure but has a positive variance. So we say those other inputs are doing something, but we reckon they're only doing about this much. Whether the active ones are doing, like making the function do this, and the inactive ones are making it do a slight fluctuation in their direction. So we are modeling them all. It's just what we're doing is we're dimensionally reducing the problem down to a much smaller level. And in fact, in many models, as you know, people put in lots of inputs into a big model, but really certain inputs are put in to correctly model a certain set of outputs. And they will obviously be clearly related to those outputs. I mean, the people who built the model would be able to tell you probably a good set of active inputs straight off. And they'll know that these other inputs over here, oh, well, these were based on this output at this time and shouldn't be that relevant for over here. So already you might be able to know just from the experts. Linear model techniques will give you a fast way, and there are far more advanced statistical methods one could use if you need to. Okay. Oh, sorry.
go ahead.
Oh, sorry. Two quick questions. The first one is, would the initial conditions be part of your input set? Because, of course, different initial condition would lead to a completely different simulation.
Yes. One of those three model discrepancy terms. I'm sorry, I didn't delay too much on the details. I wanted to show you that we'd sort of done a detailed job without leading you through the details of galaxy formation simulations. One of those model discrepancy terms looks at the fact that we actually simulate this model over several huge parts of the universe, which effectively have different initial conditions. So it's basically one huge simulation which effectively comes from different initial conditions up to a certain extent. So we can look at the variation between these pieces, and actually we're only using one sort of moderate-sized piece of that for these simulations. So we have a way in to assess some of that initial condition uncertainty. However, you can always imagine that the underlying cosmological model should be altered in a more fundamental way, and that would produce some uncertainty that we have not captured here. However, what we're trying to do is capture the core bits of uncertainty that we are aware about and we think should be there, So that were we to rule this model out, we could say definitely the physics is wrong here. Okay? But as it happens, this model fits the data quite well, so it seems like this is a consistent story. So the initial conditions we use seem like they are okay. It's sort of part of the scientific process in a sense, if you see.
And have you got a stopping rule of when to stop re-estimating the hyperparameters of your covariance function?
Yes. Well, what can I say? Just pick them. I know. So, yes, hyperparameters are a black hole of emulators. Okay, you can spend ages trying to estimate hyperparameters correctly, and there's various problems. This segregating active and inactive variables can help. Okay, because an inactive variable, the hyperparameter may shoot off to infinity because it's doing very little, may not, depending on what's going on. So that will help us. That makes our emulator problem easier. Okay. However, what we found here is that Galform actually, as many physical models are, was well mimicked by this third-order polynomial. Many physical models actually do have quite physical dependencies on the inputs, and may be well modeled by polynomials or functions of your inputs, exponentials, or functions that you know about from the structure of the model. So we found our polynomial was doing such a good job, we didn't need to worry too much about the Gaussian process part. So we picked moderate hyperparameters, which then satisfied emulator diagnostics. Okay, and we know moving those around would not affect the predictions that much. You know, maybe it may make us like slightly more efficient, but we don't need to worry too much.
Question here, then Mike.
Hi, I was just wondering, so you have this green bits and the red bits. Is there any technique to actually identify the edges between them?
Ah, right, yes. Well, I think we saw that right, and didn't David talk about that yesterday? Did we see that? We saw that in a talk earlier. No, we have not investigated that sort of stuff. I mean, our emulators are so fast, we tend to blitz the space, so we have a lot of points within the region. So maybe when we want to produce plots of it, we'll fill that region full of billions of points so we can really analyze where it is. But we wouldn't, at the moment, go out of our way to actually nail down the edge. But one can imagine one could do that. I mean, there was a talk yesterday. I'm sorry, I forget whose it was. It was David's, wasn't it? Yeah. Yeah, that's right. Yeah. And you totally nailed the edge of a region. So yeah, I would refer you to his excellent work on that.
So the method of proceeding by waves.
Yes.
Rule out more and more of the parameters. So, do I understand it correctly? There's a kind of decision problem where we decide to rule out some errors. And as we discussed absurdly in the summer school, it's basically a decision on uncertainty, right? So we have some evidence that some of the parameter space might not be good, and so we rule it out. So now I wonder, is there, or can you recuperate, if ever, the decision on the uncertainty was wrong in the beginning?
Well, yes. So a major danger is you rule as red a region which is actually quite good. Okay. Now, we set these things up in quite a cautious way. The rule we use is quite a conservative approach. Cutting at, say, 3 sigma is far more conservative than one would do if one was using a normal distribution, for example. So we try and do it in a very conservative way, backed up with serious emulator diagnostics. So, we do an extra couple of 100 runs of our emulator each wave, check that the emulator's predicting nicely for that. However, this could happen. However, one scenario is that you zoom in using this technique. You rule things out, you zoom in, and then you rule everything out. You rule everything as bad. Okay? Now, one conclusion might be that if you're doing a fully Bayesian analysis, you then need to go and find where the posterior really is. It's like you've kind of ruled out everywhere, but the posterior has to live somewhere in a fully Bayesian analysis. In our analysis, you can just end with that conclusion that everywhere is indeed bad. Now, if you think you've actually made a mistake, then you can go back, reanalyze parts of the space, and go back to there, and you have to sort of reset your waves back a couple of levels and redo things there. But the only reason you may think that things have gone wrong is that if someone has magically told you that there is a good solution there somewhere, right? So this is the difference between the fully Bayesian approach. This is the murder in the room question. If I'm convinced there must be a posterior somewhere, I need to look at everywhere very closely, okay? But if I'm convinced maybe the model is just wrong everywhere, I could rule everywhere out and that's it.
Follow-up question.
Oh, sure.
I don't think I get the argument there. So taking the ABCD perspective, for example, you would just not accept that all the samples would be above the threshold, and then your posterior would be the prior. So there is.
And would that not be a fairly how shall I say this nicely? So that would be a non-informative result, right? I mean, what you found is that you're not fitting it very well at all. Your model is very poor.
But that is the same case as with your ABN?
Yes, but then I don't need to worry about estimating posterior convergence or anything. I can rule these things out very, very quickly.
So if in ABC you thought carefully in the way Ian did about the tolerance of the metric, and if you picked a uniform prior and you had a deterministic simulator, then it reduces identically to history matching, right? So yes, ABC also has that property of being able to say your answer is rubbish, unless you do it in the way in which the nearest neighbour sense, in which you pick your 1,000 best runs, which is often done. But yeah, I agree with you. They are.
I guess what we're trying to do is give meaning to those errors so that we have some level of some way to discern what is good and what is bad. A full ABC analysis would tell you that in terms of if your tolerances just seem to be very, very large at the end of the day. But here we already know what threshold we should be expecting. So we have a meaningful kind of level on that scale to decide against.
Okay, let's thank Ian again. So, I think coffee's here, so we'll have a coffee break now, and then we'll start the 2 lab sessions, 15 minutes, have we? Yeah. So we'll have our history matching next door with Yanis and Ian, okay, and GPyOpt Python in here. So 15 minutes coffee.
Sorry, I'd like to make your lab, love to do the lab, but my research is actually on this GP stuff.
Oh, no problem.
So,
Don't worry. No.
but
I'm anticipating the majority of people will stay here because they.
No, but I'm pretty fluent on that.
Oh, right, cool,
I'd like
yeah.
to try some of the ideas that you've actually you talked about.
Sure, no problem.
You've got a package, have you?
Well, Yanis has got the code we're giving people